Carrying on from the last video where we talked about SR flip-flops and JK flip-flops, we're going to introduce D flip-flops. Now we're just going to recall the JK flip-flop. So remember that there's two inputs J and K, two outputs Q and Q inverse, and then we have this clock signal. Now when J and K are 0, Q doesn't change. When J is equal to 0 and K is equal to 1, Q goes to 0. And when J is equal to 1 with K equal to 0, Q goes to 1. If both J and K are high, the output Q will switch to Q inverse, or the opposite of what Q was. So we can make a truth table given here on the right, but the main focus is considering an example where we have two JK flip-flops tied together as shown. So we're going to have some clock signal tied to each JK flip-flop, and we're going to have JK flip-flop A and JK flip-flop B. Now we're going to have our two inputs and our outputs for the JK flip-flop A, and the outputs of A are going to be tied to the inputs of B. So what we can say is that QA is equal to JB, and the inverse of QA is equal to KB. Then we're going to have two outputs, QB and Q inverse of B, corresponding to this flip-flop here on the right. So in our time diagram, we have 6 pulses, and we're going to say that our JK flip-flop is falling edge, simply denoted by the arrow pointing down after the JK. And we're going to start with our output state QA in a 0 state by convention. So we can extend that to the falling edge of the first clock pulse. And from the first falling edge, we'll see that J is equal to 1, K is equal to 0. So we will flip to a 1. And that'll carry us through all the way to our second falling edge, where K will be equal to 1, but J will be equal to 0. So we'll flip back to 0. And then at the third falling edge, J is equal to 0 and K is equal to 0. So QA will also be equal to 0. And at our fourth clock pulse, JA will go to 1, K will go to 0, so we will flip to 1. And at the fifth clock pulse, we're going to say that JA just went to 0 and KA is high, so we're going to flip to 0. And then at that last clock pulse, we're still in the same state. So now the inverse of QA is just going to be the inverse of this signal. And now we can finally look at the output QB. So again, we're going to assume the initial state of QB is equal to 0. And now we're going to look at that first clock pulse. So you can see at that first falling edge, we kind of have this undetermined state. Because if you look at it from the left of the falling edge, you get one value. But if you look at it from the right, you get another value. So we need to remember that there's a time delay in these signals being transmitted. And that time delay is what's going to be important. And this is where we're going to fill in those vertical lines for QA and QB. So realistically, because of time delays, this is what QA and the inverse of QA would look like. Now these rising and falling slopes, instead of vertical lines, might only be nanoseconds or microseconds, but it is worth considering, especially in the case where we had different values depending on which side of the falling edge we looked at. And of course the clock JA and KA also don't have perfect vertical rise and fall times, but for simplicity we're going to say they do. So now we can look back at the clock pulses and see what's going on at the falling edge. So at this first falling edge here, we can now see that the events are triggered at these falling edges. So for this first falling edge, QA is equal to 0 and QA inverse is equal to 1. So QB would keep that state of 0. Now at the falling edge of the second clock pulse, QA is equal to 1 and QA inverse is equal to 0. So now it would shift back to a 1. But remember, there is a little bit of a delay. So now going to the third clock pulse, you can see QA and QA inverse, which are equal to the inputs JB and KB. We have the values of JB being 0 and KB being equal to 1. So we would flip back to a 0. And moving into the fourth clock pulse, we would stay in that same state because JB is still equal to 0 and KB is still equal to 1. Now from that fifth clock pulse, you can see that JB is equal to 1 and KB is equal to 0. So we flip again. From that last clock pulse, you can see that JB is equal to 0 and KB is equal to 1, so we flip back to 0. And for our third device, we can look at the D flip-flop, which you can make out of a JK flip-flop and an inverter. So how we do that is shown here on the left, and then we simply just convert that to the symbol on the right, where we have one input D and then a clock signal. Again, we have the outputs Q and Q bar, and we can make a truth table where now we have the clock and the input D. So when the clock is 0, the value of Q will not change. But when the clock is high, the value of Q will match the value of the input D. So the question becomes, are these rising edge or falling edge? Because we saw that the JK flip-flop is falling edge in the examples that we went through. It doesn't have to be falling edge, but that's just what we looked at. Now, D flip-flops can be made with a rising edge or a falling edge. But throughout history, the rising edge has been preferred. So the rising edge D flip-flop was produced more, which allowed the cost to go down, which then allowed for more people to use it because the cost went down. And it ended up that the D flip-flop is primarily a rising edge device when it's talked about. Now you can have a falling edge, but rising edge is kind of the norm. So what we can do is simply have another time diagram where we're going to move our truth table down here just so we can reference it. And we're going to have a clock signal with 5 pulses and then our input D. Now we're going to have our output Q. And because we are concerned about the rising edge of the input, we can add dotted lines accordingly. And we're going to start with our output Q in a low state up until the first rising edge of the clock. We can see that D is equal to 0, so Q will be equal to 0. So we extend that all the way to the second rising edge, where D is flipping to 1, so Q will flip to 1. Now at this third clock pulse, D will go to 0, so Q will go to 0. And at this fourth clock pulse, we're going to stay in the same state because D is equal to 0. Now at this last clock pulse, D flips to 1, so we're going to end up with Q being in a high state. And you could include the rise time slanted lines here if you choose to.